the next module, we will be looking at albedo evapotranspiration in the Arctic. So this is in continuation of the previous module where we have been talking about the albedo effect in the Arctic. So here we will also be looking at some of the examples actually seen in the Arctic region. So here is the albedo evolution of seasonal Arctic sea ice. So there is a paper in which they have actually studied this elaborately. So there are various levels of ice that is being formed in the Arctic. One is called the cold snow, then we have a melting snow, then we have pond formation. So what happens is from the cold snow to the pond formation, the temperature actually gradually increases. That means from April to June, the temperature increases, which leads to the pond formation. Then afterwards, the pond gets drained and the pond undergoes evolution, and then it leads to open water, and then from the month of September onwards, the pond again gets the water gets frozen up. So this is how the overall way it happens. This is a seasonal ice change that is happening over a period of time. And when we look at multi-year ice change, so here is the blue line which talks about the same type of transformations. So if we look at the different processes, there were some 7 processes which are given. The first one is called the cold snow. So here, before the melt onset, the snow albedo is 0.85. That means it has the highest albedo. So here in the y-axis, we have the albedo of that particular material. So here it is the cold ice which is having a very high albedo, that is 0.85. And then we have the melting snow. In the melting snow, the albedo reduces from 0.85 to 0.6. So this actually happens over a period of 7 days, and then it leads to the pond formation. So when there is a pond, there is actually water that is present there. So at that time, the albedo reduces from 0.6 to 0.35. So this also again happens over a period of 7 days. So the difference is like up to 0.32, the albedo reduces. And then it is next getting changed to the pond evolution. So here it is again getting reduced, and if you look at here, maybe in the month of August as shown here, so this leads to actually open water. The open water has the least or the lowest albedo effect, and in the pond evolution it goes up to 0.08. Here every day it decreases by small amount. In other words, the albedo keeps on reducing till it reaches the value of 0.2. And that is what we see here, and then it directly drops to the open water, and then again it freezes up later on during the winter season. So the albedo again increases up to here we have shown up to 0.4. This again increases and reaches the cold snow level, which is 0.85. So this is what is the overall cycle of the albedo with respect to snow ice in the Arctic region. So here are some of the pictures of these kind of changes which are happening. The first one is the cold snow. Here you can see it is full of ice. Then the snow starts melting. So you can see little bit of water here, and then pond formation. So here you will see more and more water that is being formed. Then the pond evolves, and finally it is again freezing up. So this is how the overall process happens within a particular season in the Arctic. And these are actually measured at the surface heat budget of Arctic Ocean Field Experiment, SHIBA. So here in the multi-year ice are actually measured at SHIBA, and the seasonal ice is actually measured in Barrow, Alaska. So these are all the 2 different places where the multi-year ice and seasonal ice, how do they change within that region and how the albedo is getting affected, those are all given here. And let us look on the effect of albedo on the seasonal ice. So what happens is during the melt season, the albedo of the seasonal ice is consistently smaller than the multi-year ice, because multi-year ice has a very thick layer of ice, whereas the new ice or the younger ice are very thin. So that's the reason the albedo of the seasonal ice are actually consistently smaller than the multi-year ice. So that means they do not reflect the sunlight very effectively. they do absorb some of the light. So when they absorb the light, what will happen actually is they start melting slowly. So that is the reason that leads to the pond formation when we have the seasonal ice. So there is an ongoing shift from multi-year ice to seasonal ice. If it happens, what will happen is this will increase the total solar heat input to the ice cover. That means more and more ice now will receive the solar radiation and it heats up the ice, and that leads to water formation. When there is water will absorb even more solar radiation, and that will again lead to a heating up of the water. So that means it is a vicious cycle where a thin seasonal ice gets melted very quickly, and it actually enhances the summer melting, and this increase in the amount of sunlight transmitted through the ice into the upper ocean. So this is how the water, that is the ice, gets reduced or ice is getting melted very quickly in the summer. So this is the seasonal change that happens in the Arctic, and this transmitted sunlight will be available actually if the top of the ice ocean is not having any more ice, then more and more sunlight will pass through the water. So this will again lead to warming of the ocean, and it also goes and it also melts the bottom of the ice cover also, and then this increases the photosynthetically available radiation for primary productivity. So there is some bad effect, there is also some good effect, because if sunlight is available, then the primary producers in the sea can actually make lots of food, so that the food web actually get a lot of food now. So the primary producer which are at the bottom can support the little bit higher level, which are zooplanktons, and the zooplanktons may be taken by the little bit higher in the hierarchy. Then it goes to birds, fish will eat the zooplankton and they get the food now, and then the fish will be eaten by the birds or mammals which are at the apex of the pyramid. So that way the entire food cycle, food web in the Arctic gets benefited if phytoplankton can actually effectively produce, that is the primary producer can effectively produce the food. So that is the positive effect. But then on the negative side, when the sunlights are hitting the water and they start warming up the water, that leads to more and more ice melting. So that is the negative effect. So here are some of the summer albedo variations in the Arctic Sea region from 1982 to 2015. So here we can see the summer month, the sea ice region, this is per decade albedo trend. So how every region, because here there are around 9 regions are given. The first one is the entire Arctic region, and then we have different segments which are present here. The CAO is basically the Central Arctic Ocean, and then we have Beaufort and Chukchi Sea area, which is given as the BC, and East Siberian and Laptev Sea is given as ESL. Then Baffin Bay and Labrador Sea is given as BL, and then Canadian Archipelago is given as CA. GS is Greenland Sea, and Kara and Barnett Seas are given as HB, KB, and then we have the Hudson Bay, which is HB. So these are all the different regions where what is the albedo trend over a decade is given here. So if you see, the effect is mostly negative except the Greenland Sea. And how do we know this albedo effects are getting changed? We can actually look at the sea ice. So if we look at the sea ice, what actually happens is, this is for the entire Arctic region, but the sea ice extent is actually having a negative number. That means it is actually getting reduced. So we can assume that throughout the Arctic region, if you look very carefully, all the regions are having less extent of ice. Less extent of ice means this will actually lead to melting of more ice. That means there are more water in the Arctic Ocean than ice. So another thing what we can understand from this is like the change in sea ice concentration also. See, one is sea ice extent gets reduced over a period of time, and here again the sea ice concentration also, because from the thick ice, multi-year thick ice getting reduced to seasonal ice. So that change is also happening. So there are two effects which are happening due to solar radiation in the Arctic region, and that can be studied using the albedo of the ice. So here again, if you look at the regions are similar to the previous one, except the Greenland sea ice, where actually the sea ice concentration had increased. Rest of the area what we have been studying, in all the places the sea ice extent or the concentration of sea ice had reduced dramatically. In fact, in the BC, that is Beaufort and Chukchi Sea area, it is minus 5.7. That means there is a drastic reduction of sea ice concentration in this area. And if you look at other places, they all have a negative sea ice concentration. It means there is a decrease in the sea ice concentration in all these areas over the period of 34 years where the people had actually studied. And there is also another thing, like how do we know sunlight, when the sunlight reaches the open waters, the temperature is going to increase. So people also measure the near surface air temperature near the sea surface. So here if you look at very carefully, in most of the places there is an increase in the number. In other words, the near surface temperature had increased. So this is actually obviously is the expected one, but through experiments we are confirming that ice reduction happens. The concentration of the ice also reduces because of more solar radiation reaching the Arctic region. And that is also confirmed by the increase in the temperature, that is near surface temperature increase also confirms that. So if you look at carefully about all the four things, and if you try to compare, the Arctic sea region's albedo was actually positively correlated with the sea ice concentration. That means more albedo is due to more sea ice. And similarly, the sea ice extent, when there are lots of ice, then the albedo is also going to be high. So there is a positive correlation between sea ice extent, also the sea ice concentration. But there is a negative effect with respect to the near surface temperature. So this is how we can actually understand how the albedo works. And the albedo is directly related to the solar radiation received by the Arctic region. Now let us look at the next important parameter, that is the effect of Arctic clouds on the ice albedo feedback. See, we have been seeing or discussing all these things assuming that there is no diffusion of solar radiation from the sun. So this is our basic assumption. But in reality, there are clouds which do exist in the atmosphere. So what are their effect? That is a very difficult question to answer, because this is the most complicated and difficult analysis to carry out. The reason is very simple. Cloud may be there today, but tomorrow it may not be there. Even after half an hour it may dissipate, or it may move to some other direction because of the wind. So that means it's very highly unpredictable to know that. But of course, satellites are there. Satellite can actually take the picture, and once the satellite can take the picture and show the information about the clouds, it becomes very easy for us to model it. What we can do is, we can do this after the event had happened, but not before the event had actually occurred. So in other words, predicting the future is going to be little bit difficult if you are going to include the cloud effect in the ice albedo feedback. Why? Because the clouds are, as we say, it may be transient. That means it has less reproducibility and accuracy. We do not know like exactly what and when it is going to be there and it is not going to be there. So Arctic is a cold desert and there is no moisture in the air. So this is the very, very important thing. When it is a desert, the probability of clouds in the desert is actually very less, because clouds are formed because of the moisture content and the dust particle if they are present. We will be looking at the atmospheric aerosol formation in the later part. So there we will understand the mechanism by which how the clouds are actually being formed. So here just we will understand that since there is no moisture, there will be no cloud. So formation of cloud is not very frequent. It doesn't mean that it will not form, but it is less frequent. And again, how much cloud affect the radiative feedback, we do not know, because again, the reflected sun rays, that albedo, is actually going towards the atmosphere. If there is a cloud, then it may stop that heat waves may be going, the radiation may be going beyond that. So cloud does two things. One, it protects the sunlight from falling down. Two, it is also blocking the radiation which is going up. So these are all the two things that may happen. And another major thing is we can actually do, as we mentioned, we can do a computer modeling. But how do we actually model this? How reliable will be the simulated clouds? Because we can simulate the cloud formation based on the satellite image. We can actually do that only after the cloud has been seen by the picture. But we cannot make a simulation where the cloud is going to be, whether it is going to be on the Greenland area or the Norway area or in the Arctic region area. We cannot easily figure it out, all these things. So these are all the challenges we have. So how do we calculate the solar radiation, observed solar radiation? So there is a calculation based on which we can actually find out how it happens. The ASR can be calculated from the radiative flux data as a product of total sky co-albedo, that is 1 minus alpha total, and the incident solar radiation at the top of the atmosphere albedo. So this is the major thing we have to know. Like top of the atmosphere is the major place from where we are actually going to do the calculation. We are assuming that 100% of the sunlight comes through that. And then the clear sky ASR can be calculated as the product of clear sky co-albedo and the incident solar radiation, if you know this number. Then the shortwave cloud radiative effect can then be determined as the total ASR minus the clear sky ASR, because we have to see what is the total one, and if there is a cloud, then how much is the amount which is getting reduced or removed due to the cloud. So these are all the things we will have to include while we actually calculate the total observed solar radiation. So because the clouds have a significant role in reducing the radiative feedback, that means whatever is escaping the atmosphere is actually being blocked by the cloud. So that is the reason we do need to know how much of the cloud is there and what is the thickness of the cloud, everything we need to know, because it reduces the radiative feedback by around 50% in the summer due to the cloud masking effect. Although cloud has nothing to do with sea ice loss. See, the sunlight comes and it starts melting the ice, can happen whether cloud is there or not there. So that is what we have to know. Only it will, the feedback, that is the radiative feedback, is getting affected because of the cloud, not the solar radiation that is hitting the Arctic ice. So there is a possibly negative effect of cloud on the ice albedo feedback during the midsummer month because of cloud.